Last year in Math 20-1, you studied how to solve what are called radical equations, and you solved them algebraically. And the objective in this course is that you know how to solve them graphically. However, and I don't want to delve too much into trying to figure out the mind of Alberta Learning and the diploma exam, there are certain questions on the diploma exam that would require your understanding of how to solve these equations algebraically. Even though this course, the curriculum, says you just need to know how to solve them graphically, solving them algebraically is the only way to solve some problems, and to be quite honest, it's quicker to solve things algebraically sometimes than it is graphically. So we're going to review the algebraic methods of solving these equations from last year, including the identification of what are called extraneous roots. And this concept of an extraneous root is something that you learned about last year, but it's going to crop up in, I'm counting in my head, I think at least 3 different places in this course, where what you do is you solve an equation properly. You don't make any mistakes. Your math is pristine. It's golden. But the answer you get doesn't work. Okay? And one of the things we need to get used to is whenever you're solving radical equations, you have to consider the possibility that the solutions you get don't work. Maybe. And if they don't work, what we call them is an extraneous root. The word root means solution. The root of an equation is the solution to the equation. I've always kind of taken issue with saying an extraneous solution because it's not a solution. It's not correct. It doesn't work. So remember, when you solve an equation, you're finding a value for the variable that makes the equation true. Bottom line is you have to check your answers, and we'll go through that when the time comes. We're also going to be using graphical methods to find approximate solutions, and there are a couple of different ways that we can explore graphical approaches to solving equations. To begin with, let's take a look at the first equation. Example 1 says state the restriction on x in this equation. This equation contains a radicand. This is a radicand. That's the word we use to describe the thing that's underneath a radical sign, a square root sign. And it's always the case. Well, there's a little exception to this that I haven't decided right now if I want to show it to you today or not. But for the time being, what we want to do is we want to say that the radicand always has to be greater than or equal to 0. And the reason for that is a radical sign means you're going to take the square root, and you cannot take the square root of a number that's negative. Okay? The bottom line is the restriction on x can be found by solving this inequality. X plus 10 must be greater than or equal to 0, and that means that x must be greater than or equal to negative 10. And now, well, let's put this on a number line just to make sure that you understand what it is we're saying about that restriction. What we are saying is that values of x that are equal to negative 10, that are equal to negative 10 or greater than negative 10 are allowed to be put into the equation. Okay, listen very carefully to the words I'm saying, though. I'm saying you were allowed to put them into the equation. I'm not saying they will make the equation true. There's a distinction there. So the values of x that are allowed to be put into that equation are any numbers that are greater than or equal to negative 10. Now I have to address something from Math 20 that is a serious mistake. And I don't know if Math 20 teachers make the mistake or not, but it's made in the textbook. Okay? And it's just wrong. When we talk about solving this equation, this restriction is not helpful at all. Okay? What the Math 20 textbook basically says is if you solve an equation and you get a value for x that's in this domain, that it's correct. And I'm telling you that's not true. Just because the solution you get is in this domain doesn't mean it is a correct solution. It could be extraneous. However, if you solve an equation and you get a value for x that's outside of this domain, you know for a fact it's not a solution. But just because it's in doesn't mean it is a solution. And in Math 20-1, they make a big deal of how important this restriction is. And it's not important at all in solving the equation. It isn't. Okay, we're going to see at least one example where that's the case. So now we're going to solve this equation algebraically. Remember what I've tried to teach you in Math 20 if you had me as a Math 20 teacher, and in this course. When you simplify an equation, the word simplify means to express it in a simpler form. But what does that mean? It means express it as an earlier math problem. Right now, if you're looking at this problem, if you were a grade 9 student, this radical is troublesome because you don't know what to do with it. So if we can get rid of the radical, we can turn it into a grade 9 equation, almost. And that's going to involve isolating the radical. Well, I take back almost. It will turn into a grade 9 equation here. It'll turn into a grade 5 equation in a second. We're going to isolate the radical, and what that allows us to do is to square both sides. So, in a very general sense, when we're solving equations, and we've had long conversations, those of you that are in calculus right now about this, you want to do things like get rid of radicals, get rid of fractions, get rid of decimals, get rid of those things that are in equations that make things complicated. And if you get rid of complication, you get simplification. And that's what the word simplify means. When you square a square root, you get x plus 10. When you square 4, you get 16. So this is now, as I said, a very simple equation to solve. If it were a written response, you would probably write minus 10 on both sides of this to understand or to demonstrate why you get x equals 6. But x equals 6 is the answer we're getting. Any questions with the algebra there? Pretty straightforward. This is what you did last year in Math 20. What we want to do is now check. And when you check, what you want to do is do a 2-column check. LS means left side, RS means right side. And you always want to go back to the original equation. So on the left side, we have the square root of x plus 10 minus 4. And on the right side, we have 0. We don't put equals there. You're checking to see if they're going to be equal, so you can't start off by saying they are equal. And the solution we get is 6. Pretty straightforward stuff here. We're going to take that 6 and we're going to pop it in there and make sure that we get the same thing on the left side as we do on the right. When I do that, I get the square root of 6 plus 10 minus 4. I don't have to keep writing 0, 0, 0 here. I'm not doing any work with it. The right side is 0. That gives me root 16 minus 4. Root 16 is 4 minus 4, which is 0. And that means that the left side is equal to the right side. We've demonstrated that. And you would actually need to show that on a written response. By the way, nobody is asking, but I'm sure some of you are wondering, why is there no plus or minus? Because the principal square root means the principal square root. It doesn't mean plus or minus. The only time you have plus or minus is if you introduce it by taking the square root of something. The square root symbol was already there, so there is no plus or minus. Any questions with B? All right. Again, this is a bit of review. Find the x-intercepts of the graph of this function. So what we're asked to do is take our graphing calculator and graph y equals the square root of x plus 10 minus 4. I hope it's not lost on you that the square root of x plus 10 minus 4 is what's equal to 0 in the equation. So what we're doing is we're going from solving this equation, 0 equals the square root of x plus 10 minus 4, we're going from solving an equation to analyzing a graph. These are two different things. I mean, they're connected. We're going from solving an equation to finding the x-intercepts. And before we do that, of a function, before we do that, and I know that some of you already have it graphed, I want to point out to you that if this were a Math 20 class, and I said to you, find the x-intercepts of that function, what you would do is you would say, well, an x-intercept is wherever y is 0. Correct? You would change that y to 0. Well, then you would be solving this equation. And the point I want to make in a very general sense is the x-intercepts we get have to be equal to the solutions to the equation. That's always going to be the case. It doesn't even matter what type of equation it is. If the equation is an expression equal to 0 and you graph y equals that expression, then the x-intercepts of that function will be the solutions to the equation. So just to verify that, y equals the square root of x plus 10, close the brackets on the argument for the square root, and then subtract 4. I suppose you could understand what this is going to look like based on transforming root x, but we're just looking at the graph here. I'm going to go zoom 6. I can see it's crossing the x-axis over on the right-hand side. Just to see that a little better, I'm going to change the zoom settings or the window settings. I'm using zoom box here to get a better picture of what's inside this long rectangle that I've got. You can see that it's crossing the x-axis. To find the coordinates of that point on the x-axis, you go to your calculate menu, which is second trace. You choose 0. This is interesting. Why do you choose 0? Because you're finding out where the function is 0. That's what an x-intercept is, where y is 0. You're tasked now with moving the cursor to the left of that x-intercept, and then you have to move it to the right. And then you hit enter, and it says guess, and I don't really know the reason why your calculator is programmed that way, but I never guess. I just hit enter, and I get 6. So what we notice is the solution to the equation is x equals 6, and the x-intercept is at 6, 0. We notice, and I'm not going to write it down, you should write it down if you feel you need to, that the x-intercept of the function is equal to the solution to the equation. And you know, before we go on, I want to point this out to you. No matter how complicated the equations get, if you're stuck on an exam and you just want a decimal answer, you can do this. Even if it's trigonometric or logarithmic or exponential or whatever types of equations we're going to be studying. I want to show you a different way to do this. And I prefer to solve this equation graphically. If I had to solve it graphically, I wouldn't do it with x-intercepts. I find determining x-intercepts to be clunky sometimes, awkward, because the graph sometimes is very steep as it goes through the x-axis, and putting the cursor to the left and the right is problematic. Because you scroll a little bit to the right, and it takes off in a vertical direction. So what I would do, if I wanted to solve this equation graphically, is I would arrange it for it not to be equal to 0. I'm going to add 4 to both sides. And my thinking here is that I'm going to graph this as y1 and this as y2. And I'm not interested in x-intercepts. I'm interested in where they intersect each other. Intersect, not intercepts. If I do that, look what happens here. I'm going to get rid of the minus 4 here. I'm going to graph y equals 4. I'm going to go back to zoom standard. And the beautiful thing about this is as long as I can see the point of intersection of the two functions, and as long as I only have two functions, here's what you do. You go to your calculate menu, you choose intersect, hit enter, and then you hit enter 3 times. You don't need to scroll around. First curve, you can see at the top of the screen, first curve is y1, enter. Second curve is y2, enter, guess, I don't want to, and you end up with the point of intersection being 6, 4. So the x coordinate is the solution. X equals 6 makes them equal. That's just my preference. All right, let's take a look at example 2. What is the restriction on x in this equation? Well, the radicand must be greater than or equal to 0, which means that x must be greater than or equal to -5. I'm a big fan of a number line kind of interpretation here. If this is -5, allowable values of x that you can put into the equation, not necessarily making it true, are any values of x equal to -5 or greater than -5. Okay. Pretty straightforward, I think. Any questions with A? All right. This is in the unit handout from last unit. Page 39. So now we have to solve this equation algebraically. Luckily, the first step is already done, everybody. The radical is by itself. That's what you have to do first, because what you're going to do is square both sides, and the only way you can get rid of a radical when you square both sides is if it's by itself. So I'm going to rewrite this. Whoops. I'm just going to throw a set of brackets around the x plus 3. That way I can write squared. You don't really need the brackets around the radical. You can do that if you like. What happens when I square the left side is I get x plus 5. When I square the other side, don't forget, you don't want to make, a rookie mistake of thinking that you can just square the x and square the 3. X plus 3 quantity squared means x plus 3 times x plus 3, right? So we have to FOIL that out. You're going to get x squared plus 3x plus 3x plus 9. I will sometimes speak to the Math 31 students in the class because I have a number of them in here. Just to let you know my thinking here, in this class I would probably write 3x plus 3x, but in Math 31 we would just write 6x right out of the gate. And many of you would probably just do that. One of the things you observe here is it's quadratic. The resulting equation we get is quadratic, which takes us to Math 20, where you're taught that to solve any quadratic equation, you zero the equation. You always zero a quadratic equation. Well, unless you want to complete the square, but I don't think anybody really wants to complete the square to solve an equation. Since I have positive x squared on the right, I'm going to leave my x squared there. I would like to deal with positive x squareds. I don't like negative x squareds. I have 6x on the right, and I'm going to subtract the x from the left, which will give me 5x on the right. And then I have 9, and minus the 5 on the other side will be plus 4, and this is equal to 0. There are different methods that you can use to solve a quadratic equation from this point. I would always recommend factoring if it's possible, because that's your quickest direct path to the answers. Since the coefficient of the x squared is 1, if this factors, it's going to factor into two binomials of that form, and it will factor if two numbers multiply to give 4 and add to give 5, and they do. The numbers that do that are plus 1 and plus 4. And that means that x plus 1 equals 0 and x plus 4 equals 0. We haven't done a lot of work with quadratics yet this year, but the reason for that is if you have those two factors multiplied by each other, anytime one of them is 0, it doesn't matter what the other is. When you multiply that other by 0, you'll get 0, and that's what we're after. This is equal to 0. So if either of those factors are 0, the product will be 0. We solve each of these equations and we get x equals -1, and we get x equals -4, but now we have to check for extraneous roots. So we go back to the original equation. We're doing a left side, right side approach. I think on the left side was the square root of x plus 5. Can somebody give me a nod or a thumbs up if that's the case? Okay. And the right side was x plus 3. So I'm going to have to do this for both of these solutions. Well, both of these answers. I don't know if they're solutions yet. So root x plus 5 and then x plus 3. So my first solution, I'm talking here about the x equals -1. We're going to put -1 in for x and get -1 plus 5 and then -1 plus 3. Sorry, we get square root of -1 plus 5. Underneath the square root, -1 plus 5 is 4. So we have root 4, and over here we have -1 plus 3, which is 2. Root 4 is 2. Okay, the left side is equal to the right side. So what does that tell us? It tells us that x equals -1 is a solution. And I think it's worthy to note, if this were a written response, you would write something like that. You wouldn't just, some people would just put a check mark beside it and go, yep, that's right. No, you need to say it is a solution because it passed the verification process. If we do the same thing here with the -4, what do I get? I get the square root of -4 plus 1. And here I get -4 plus 3. Well, -4 plus 3 is -1. -4 plus, pardon me, plus 5. -4 plus 5 is 1, so I get the square root of 1, which is 1, and the left side is not equal to the right side. And that means that the value for x at the top, this, is not a solution. Now, let me point something out to you. So there's only one solution. Let me point something out to you. If you go back and you look at, I think, part A, didn't we find the restriction? And the restriction was, I'm going to go to a new page for this. This is what we had for the restriction. For x. The two numbers we got for x were, correct me if I'm wrong, -1 and -4. Is -1 in this domain? Yes. -1 is maybe over here. -4 is over here. Both of these numbers that we got are in the domain. And the mistake that your textbook in Math 20 makes in at least one place is it says, if that's the case, they're both valid. And they're not both valid. They're both numbers you can put in for x, but only one of them is a solution. And it's why I've said that this piece of information is really of no value in solving the equation. It doesn't really mean anything. Anyway, we only have one solution, x equals -1. Let's solve this now graphically. And I've got two methods here that we're going to use using intercepts. What that means is you have to zero the equation. You have to zero the equation by subtracting x from both sides and subtracting 3 from both sides, and then graph y equals. and look at the x-intercepts. This is the x-intercept method. So I'm going to graph, and again, I prefer the other method, but we'll do it this way first. The square root of x plus 5, close brackets, minus x minus 3. You know, zoom 6 is always your safest bet. I can see some kind of graph. Don't try to figure out what that graph looks like or why it looks like what it looks like. It is what it is. You know, you probably, or I probably should have verified that I typed it in correctly before I committed myself to looking at the graph, but it's fine. I can go to my calculate menu and choose 0, scroll to the left of that x-intercept and hit enter, scroll to the right and hit enter, then hit enter a third time. You can see -1 is a solution. Remember our other solution was -4? Well, our other, solution in air quotes was -4. Does this graph actually cross the x-axis at -4? No. So it's extraneous. And that's an important point. You don't see the extraneous solution on the graph, which can be a good thing or a bad thing. The reason it's a good thing is if you want to know the answers, you just look at the x-intercepts. The reason it's a bad thing is this. On an exam, sometimes you're asked, what is the extraneous root? That's the diploma exam kind of question or unit exam kind of question that you have to solve algebraically. You're not going to know that it's -4 unless you do it that way. If you use the other method, then I'm just going to graph y1 equals the left side and y2 equals the right side. This is my preferred method. What do we got here? Root x plus 5 and then x plus 3. Graph. Now I'm going to get two graphs, and I'm interested in where they intersect. So I go to my calculate menu and choose intersect and hit enter, 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 -1. I don't care about the y coordinate, I care about the x coordinate. So, I mean, no matter how you cut it, that's the solution. And we found it graphically. We don't need to look at the domain restriction for the radicand. We don't need to look at at extraneous roots. If you want the answer, graphically is a pretty quick method. What do you notice about the extraneous root found when you solve the equation algebraically compared to when you solve it graphically? I'll leave it to you to write this down if you like. You don't see the extraneous root because it's not a solution. It's not a solution. I would have preferred, if I could go back in time and be king in all that is math, to just tell everybody, you know what we're going to call extraneous roots? Incorrect answers. That's what they are. I understand that's not really that great of an idea because you've done everything correctly, but you get the wrong answer. It's just not an answer. Let's take a look at another one. Solve this equation graphically, or algebraically first, rather. So we have to square both sides. Because the radical is already by itself, it's already been isolated. When I square the right-hand side, I'm going to get x squared plus 4x plus 4x plus 16. Because x squared, because x plus 4 squared means this. So I have to FOIL it out. When I square the other side, I get 3x squared minus 5, because when I square a radical, the square and the radical are inverse operations. They just cancel. I'm going to zero the equation now by subtracting x squared from both sides, by subtracting 8x from both sides, and by subtracting 16 from both sides, getting that, which I'm going to double check all of my work. How's that look, you guys? Okay, good. And you know, when I say that, again, I think you know me by now, but I'm saying that to get everybody to just stop and stop writing and copying what I'm doing and look at the math and think about the math. I have so many math things floating around in my head from the different classes, so I don't know that I've discussed this with this particular class. But in Math 20, I make a big deal of talking about the significance of b squared minus 4ac in terms of factoring. Have I talked about this in this class? I have. What's the significance here? Well, let's calculate b squared minus 4ac first. That would be negative 8. Don't forget b is the coefficient of x squared minus 4 times 2 times negative 21. So I have to figure out what that is. And I want to say 232, but I just ran that through my brain fairly quickly, so I'll give you a second to double check. 232. Starting to see some nods here. So the discriminant, which is b squared minus 4ac, is 232. What's the significance of that number in terms of my ability to factor that quadratic expression? What does that tell me about the ability to factor it? Miles, do you remember?
It's unable to factor.
Right. Why is it not factorable?
It's not it's not like...
Can you give me an example of a number that this would be where it would say, oh, okay, factor me?
64. Any number that's square.
Square, perfect square. So if we get 1 or 4 or 9 or 16 or any of these perfect squares, it's factorable. That means that this is not factorable, so here's our friend off of our formula sheet. The quadratic formula is what we're going to have to use. The nice thing about this is negative b would be positive 8 because b is negative 8. The nice thing about this is we've already done a lot of the legwork. We have to go plus or minus the square root of the discriminant, but we've already determined that. It's 232. And this is over 2a, which is 2 times 2. So we end up with x equals 8 plus or minus root 232 over 4. Now, you know, unfortunately, by the time you get to Math 30, you have all of this other stuff weighing on your mind from going all the way back to, you know, even grade 7 or earlier up to last year. And one of the things you're expected to know how to do is to simplify that expression. So on the side somewhere, we need to explore how we can simplify root 232. And this goes back to actually to grade 10, but you practiced more in grade 11 last year. What we want to do, and I want you to listen very carefully to this, because this can be a little tricky, is we want to break up 232 into a product of two numbers, one of which is a perfect square. Okay? Like 4 or 9 or 16 or 25 or 36, etc. But our job will become quicker if we can find the biggest perfect square that divides in there. So if I were doing this, I would say, well, 232 is an even number. So I'm going to see if it's divisible by 4, which is a perfect square. So I go 232 divided by 4. And I get 58. And then what I say is, well, is 58 divisible by another perfect square? Because if it is, then I want to get both of those perfect squares out. But I don't think 58 is. 58 is 29 times 2, I believe. And what that means is that 4 is the largest perfect square that divides without remainder into 232. It goes in 58 times, which means this is 2 root 58. And we can go back over here and change that root 232 to 2 root 58 and get this. Now, one of the other things you should know about me by now is we have all this content we learn about, but I'm always using it to teach you math. Forget about radical equations. Forget about extraneous roots. Let's talk about math. Am I allowed, and the fact that I'm going to say don't do this tells you the answer is no. Why can I not just do that and write 4 plus or minus 2 root 58 over 2? Actually, I could go even further. I could go 2 over 1. Why am I not allowed to do that, though? Seamus?
Because you aren't dividing the radical by the same amount.
Right. I need to divide the radical by the same amount, which will mean dividing the coefficient. And there's a deeper reason why I need to do that. So first of all, I do not really have a problem with people going from this to the answer, which is 4 plus or minus root 58 over 2. What I'm doing is I'm dividing each of these by 2. So the 8 becomes a 4, the 2 becomes a 1, the 4 becomes a 2. I don't have a problem with you doing that, but there's a deeper reason why you have to do that. And it's because, and definitely we talked about this a lot in Math 31, you are only ever allowed to cancel things if they are factors of the top and the bottom. So if I take a look at this top of this expression, I can factor a 2 out and have 4 plus root 58. On the bottom, I have a 4, which is 2 times 2. And factors, have I really driven this point home in this class yet? I don't think so. Factors are things that are in brackets multiplied by their surroundings. So that 2 on the top in green brackets is a factor of the top. The 2 on the bottom in green brackets is a factor on the top. And that means that I can cancel those two 2's, giving me the answer. You're only ever allowed to cancel things that are factors. All right, what does this mean? Let's get back to the specific topic. It means that 4 plus the square root of 58 over 2 is a solution, maybe. And 4 minus the square root of 58 over 2 is a solution. We need to check them for their extraneousness, if that's a word. I don't know that it is. And I don't really feel the need to write all this down. I'm going to go back to the original equation. Was the left side of the original equation 3x squared minus 5 under a square root? Okay. And was the right-hand side x plus 4? Okay. So here's what I'm going to do. And you can manipulate your calculator in a lot of different ways. I'm going to calculate what this is first by taking 4 plus root 58 and then dividing by 2. And I'm going to store that, I hit my store key, as alpha A. All this means is anytime I bring up the letter A until I replace it further down the road or reset my calculator, it's going to use that value. So I'm going to take the square root of 3 times A squared minus 5. I'm going to figure out what it is. I'm also going to take, the other side was the solution x plus 4. Yeah. I'm going to take A plus 4. Okay. So 4 plus root 58 all over 2. I didn't mean to put plus or minus here. Should just be plus. 4 plus root 58 all over 2 is a solution. If I try 4 minus root 58 all over 2, okay, well, I'll just go back up here. And just change this to minus. Probably could have typed that in quicker than scrolling. Divided by 2, I get this for a solution. I'm going to put that in for B. I could put it back in for A. It doesn't really matter. And take the square root of 3b squared minus 5. Did I get that right? 3x squared minus 5 under the square root sign. Okay. My left side becomes this. I'm also going to take my supposed answer and add 4. And I get that. They're both solutions. So both of these are valid. Solve this equation graphically. Again, I wouldn't worry too much about what the graph looks like necessarily. I'm not going to go with the x-intercept method. I'm going to go with the intersection point by graphing the left side equals the square root of 3x squared minus 5, and the right side, y2, is going to be the graph of x plus 4. Zoom 6, whoops, zoom 6, there's the square root function. You can see that that line of x plus 4 cuts the graph in 2 places. I'm not going to bore you with the details, but when you find the x coordinates of these 2 points, you will get 4 plus or minus root 58 all over 2. By the way, when you do this, you can't get an exact value on your graph. You'll only get decimals. One last example to go. By the way, this is a very quick way of verifying that both of these answers had to be correct because there's 2 points of intersection. Right? Final example. Speed of a roller coaster that has an initial speed of v0. So v0 in this question is the initial speed, and d is the distance. The speed at the bottom of the distance traveled is given by this. And the question is, if the initial speed is 8 and it reaches a speed of 130 feet per second at the bottom, and the value of A is 32, what's D? That's what the question is. The question is, solve this equation. Now, this is going to be very quick. It's not going to take a long time, but I want to just stop for a second. If you cast your mind back to using your graphing calculator, say in grade 10 or even last year or maybe even this year, do you agree that one of the most frustrating things sometimes is to get the right window settings? It can be very complicated. And when the time comes where that's important, we'll talk about some strategies. For that reason, I think by the time you fiddle around on your calculator trying to find the right window settings here, you could solve this algebraically very quickly. I mean, really, if you square both sides, look at what happens. I think you get 16900, but I'm pretty confident on that, but I would like somebody to double check it is. And what you get on the other side is 64, because 8 squared is 64, plus, well, coincidence, 64d, because that squaring of the right side eliminates the radical. You've turned this into a grade 7 or 8 math question right now. I mean, you just have to take 16,900, subtract 64 to get 64d, equals 16836. I'm pretty sure that's right, but
wrote 2 instead of 6.
Thank you. Thank you, Miles. Is it, in fact, 16836, though? Okay. So now I divide both sides by 64. It's a childlike problem once you get to this point. So D will be equal to 16836 divided by 64. So about 200. Oh, no, that's feet. That's feet, right? I was thinking I'm stuck in meters because we normally work in meters, and I thought that doesn't seem right. That's 2.5 football fields for a drop on a roller coaster. But it's not. It's feet. So the answer is 263 feet. One of the things that comes out of this lesson, of course, is a review of the quadratic formula, which you were expected to know how to use. Normally on the Unit 1 exam, there would have been something that would require the use of the quadratic formula, but because we didn't have this lesson until after the exam, there wasn't anything there. From now on, any equation that devolves into a quadratic equation is fair game, whether it's factorable or not factorable in this course. You need to be able to carry that forward from Math 20-1. There are some questions in your textbook and handout dealing with solving radical equations.